Hello, denizens of the deep. We're continuing in chapter 7 and finding eigenvalues and eigenvectors. This little box here kind of summarizes the techniques that we've been doing, and so we're going to use this and get some cool stuff. So we're going to find the eigenvalues and the eigenvectors of this matrix here, and you may have noticed that this matrix is diagonal. So when I do lambda I minus a, which is what I taught you in the previous videos, so I get lambda minus 2, -1, 0, 0, lambda minus 2, 0, 0, 0, lambda minus 2. And when I take now you know that this is a triangular matrix. So when I take the determinant is just going to be the product of the main diagonal, which is just going to be lambda minus 2 to the third power. So our characteristic equation is lambda minus 2 cubed equals 0. Well, I don't have to, normally I would multiply, well, I don't have to multiply anything out. I mean, obviously the only eigenvalue is lambda equals 2. And now we want to find the eigenvectors of lambda equals 2. So we're going to solve, to do that, we need to solve the homogeneous linear equation represented by 2i minus a equals 0. Now, where did that 2 come from? That 2 came from this 2 right there, or that 2 right there, whichever you want to say it. So, anyway, 2i minus a. So 2i minus a winds up becoming this guy right here. It's kind of cool the way. Let's just look at a again. See, that's a. When I multiply I by 2, I get 2, 2, 2, 2, 2. And when I subtract, basically the zeros just stay zeros. The 2's are going to disappear, and I'm left I'm left with minus 1. So that would mean that if I set this all equal to 0, that would mean that x2 is equal to 0, and that column 1 and column 3 don't have any leading ones, so that they would just be s and t. So basically, my solution is going to be so the typical vector in my solution set will be x1, x2, x3. X1 is just the parameter s. X3 is a parameter t, and x2 has to be 0, which is s times this plus t times that, and that would be a typical solution. So now, if you notice, lambda equals 2, this eigenvalue has 2 linearly independent eigenvectors. So therefore, I say the dimension of the eigenspace is 2. Not 2 because of that 2, but because of this 2, that there are 2 independent. I also want to say that what this means is that basically any vector in R3, which with a y equals 0, the middle variable is 0, that's going to wind up being a solution for this, for the eigenvalues. Anyway, there you go. We've just found the dimensions of an eigenspace. Okay, now if you notice, whenever you have a lambda that occurs several times, like the previous example, we had the eigenvalue 3, and the eigenvalue lambda equals 2 in the previous example, and it occurred 3 times because it was lambda minus 2 to the third power. So we say that it has a multiplicity of 3. That's what it means when we say. By the way, we use similar terminology in general with polynomials. Anyway, also note that the dimension of the eigenspace is 2. So usually the multiplicity of an eigenvalue is greater than or equal to the dimension of the eigenspace, which is funny because personally I always think of this the other way around, that the dimensions that the eigenspace is going to be less than or equal to the eigenvalue, but the same thing. The dimension of the eigenspace is going to be less than or equal to the eigenvalue, or you could say the eigenvalue is going to be greater than or equal to the dimension of the eigenspace. So we saw that in the previous example, and we're going to, that's generally how it works. So let's find the eigenvalues this matrix. Here's our matrix right here. And we want to find the eigenvalue, and we want to find a basis for each of the corresponding eigenspace. It means each eigenvalue is going to have eigenvectors, which is going to form an eigenspace, and we want to find the basis for each eigenspace. Now, sometimes it only has one eigenvector, so it's a one-dimensional. It's not such a big, not that hard one. But anyway, let's just do it. So we want to do lambda I minus a. So lambda I minus a. So basically, so it comes out looking like this, because lambda I is, again, that's a matrix that has lambdas down the diagonal and everything else is 0. So it's lambda, so it basically becomes everything that's on the diagonal is lambda minus that thing. Lambda, that's 1, that's lambda minus 1. That's 1, that's 2, that's lambda minus 2. That's 3, that's lambda minus 3. Everything else is going to be 0 minus that thing. So that's 1, that's 0 minus 1, which is negative 1. That's negative 10. Then this is 0 minus negative 10, which is positive 10. Of course, 0 minus 0 just stays 0. So the 0 stays 0, everything else. So basically, the 0 stays 0. Everything that's off the diagonal becomes negative of what it was before. Everything that's on the diagonal becomes lambda minus that thing. Anyway, if I would take this determinant, multiply everything out, you could do this. And by the way, if I was going to do this determinant, if I was me, I guess I would start probably with the first row, because it's so many zeros, and then you just have to take the smaller determinant. And to take the smaller determinant, I would go down that first column because you have these two zeros and whatever. It's always nice to do things as easy as you possibly can. But when you do that, if you do this correctly, you're going to wind up with lambda minus 1 squared times lambda minus 2 times lambda minus 3. So we have the eigenvalues are 1. Now, does that mean that the eigenvalue 1 is going to have a two-dimensional eigenspace? No, it means that it's going to have at most a two-dimensional eigenspace. This lambda value of 2 is going to have at most a one-dimensional, and lambda value of 3 is going to have at most a one-dimensional. Anyways, let's continue. So we're going to go through one by one. So we're gonna so our first lambda is 1, our second lambda is 2, our third lambda is 3. We're gonna go through it one at a time. So if we plug in 1, so I minus a gives us this matrix, which if I put this into reduced row echelon form, it becomes this sucker right here, and this is a two-dimensional. As you can see, this is a two-dimensional thingy ding. I let this column has no leading ones. The second column and the fourth column have no leading ones. That's going to be my S and my T. So I wind up getting that my X vector, this is something we've done a bunch of times, is going to be S times this sucker and T times that sucker. And these guys right here is my basis for the vector space. These guys here is my basis for the vector space. So let's so we see that lambda 1, which is the eigenvalue 1, has a two-dimensional eigenspace. Means there are two eigenvectors or two bases, whatever, you get the point. So it's a two-dimensional eigenspace, and here's the basis. Now for lambda 2 equals 2, we're over here. For lambda 2 equals 2, and lambda 3 equals 3, you do the same thing. And you get here's the basis for B2 for lambda 2. That's the basis for lambda 3, and pow. And again, we're doing the same thing that we've done many times before. Constantly more efficient to use American method of processing. Okay. I was just looking at this interesting note over here. Okay, moving on. The eigenvalues of a triangular matrix. Now, a triangular matrix, as you remember, that's when you have there's upper triangular and lower triangular. That's a triangular matrix is when you have all zeros. One side of the diagonal has all zeros, and depending on which side it is, that'll be the upper or lower, triangular. Anyway, so if A is an n by n triangular matrix, the eigenvalues are the entries on its main diagonal, which means that here we have some triangular matrices. So notice that this is triangular. So the eigenvalue is going to be 2, 1, and -3. And this sucker is very triangular. This is like super triangular because everything is 0 off the main diagonal. And so the eigenvalue is going to be -1, 0. 0 can be an eigenvalue. So we said you can't have the 0 vector as an eigenvector, but the scalar 0 can be an eigenvalue, -4 and 3. And let's say we didn't use the theorem. Now we just use that theorem. It's like, to me, using theorems is like cheating. I like to work these things through. So suppose we worked it through. We did lambda I minus a, and we got this sucker right here. Well, if I would take the diagonal, notice I still have a triangular matrix here. So the diagonal is just going to be lambda minus 2 times lambda minus 1 times lambda plus 3, which gives me 2, 1, and -3, which is what we had on that main diagonal. So it's going to work. And here, this is like, when I do lambda I minus this guy, I just get a lambda plus 1, a lambda minus 2, a lambda plus 4, and lambda minus 3. So that's going to give me my lambda values are going to just want to be -1, 2, 0, -4, and +3. And again, I can solve these to find all the different vectors and so on and so forth, but that's not what I want to do at the moment. This is interesting here about using eigenvalues and just some interplay between eigenvalues and differential equations. That's kind of cool and has to do with flasks and membranes and kind of cool stuff. All right, moving on. I think I'm gonna stop at this point, and next time we're gonna do eigenvalues and eigenvectors of linear transformations. Okay, so let me stop the share. Let me stop the recording.